Okay. All right. So we started differential equations. You guys should be familiar with this. You've seen it in other classes. What we're going to talk through a little bit here today is kind of picking up with where we were. All right. You guys are probably largely familiar with Laplace transforms, like we said the other day. So we're not really going to focus on Laplace transforms. We're going to focus on the approach where we have a particular solution and a transient solution and all that. We're going to go through that. All right, so I'm going to pick up with the example that I was talking about the other day and the process we were using. So I talked about this difference between static and dynamic systems. In both, we're going to think about things in this class just like you do in signals and systems, which is to say I have inputs and outputs, right? So in this case, in the systems I have here, my input in both cases, here I have a voltage source. This is my input. My output would be the current here. And this system over here, the output is also going to be let's say the current flowing in this circuit. What's the difference between the one on the left and the one on the right? What was my name for this guy on the left versus the one on the right? Static, right? This guy is static. And this guy over here is dynamic. What's the meaning of that? What's true about the current in that static system? It's constant. As soon as the voltage source turns on, the current gets to its steady state value. Whereas in the system over here, what's the steady state value of the voltage on that capacitor? And what's the steady state value of the current in the circuit? 0. Right now, if that capacitor was charged up to some value, then there's going to be a current initially. It's going to be gone, right? But there's a time varying component to that, right? In this case, I of t varies with time. And that static circuit, it doesn't. As soon as I turn the power on, there's a current flowing, and it's always the same. All right. So basically, whenever I have dynamic systems, I have energy storage. And what I said is there's always two parts to the response. Right? There's a steady state response, which is the part that comes directly from what I would call the input to the system. Right? There's a steady state response that comes from the input to the system. Now, over here, somebody said the current was 0 in this circuit over here, right? What's the input to the system in this particular case? In that circuit on the right, what's the input?
The capacitor.
Well, there is no input, right? There's no, when I say an input, there's no source. Now you're correct. The capacitor is doing something here, right? But the other piece is the fact that there's a transient response. There is this fact that the energy stored in this capacitor doesn't want to change instantaneously. So there's always two parts to our response. There's a response that comes from the input, and then there's a response that reflects this, what I said, finite amount of time it takes for the energy to change from the initial state to the final state. So it's valid, I think, for somebody to say that the capacitor is the source here. It's not, it's the source in some sense, but there's no power supply in this circuit. There's no power source that's going to cause anything to happen. The fact that there's charge on that capacitor is going to cause something to happen, but I really think of that as the second piece here. The fact that there's a response that reflects the finite amount of time it takes for the energy to change. So there's always those two pieces that exist in these things. So what we said last time is that the basic approach we're going to use here is in 3 steps. All right, step 1 is basically I solve what I call the homogeneous equation. What the heck is the homogeneous equation? Yeah, you take the differential equation, you set it equal to 0, right? And we call that response the homogeneous, transient, or complementary solution, okay? And in the homework, you're going to see I call that y sub c, all right, which is consistent with the way the book calls it in chapter 7, all right? Now, the other piece, this non-homogeneous equation is whatever the equation is equal to whatever it's equal to, all right? We call the solution to this guy the particular solution or the steady state solution, all right? So steady state is another term for this one. And I usually use the term steady state and transient, all right, because they have more of a physical meaning to me. All right, we use this, what we call undetermined coefficients method. All right, what does that mean? I guess I don't know if I clearly defined that the other day. When I'm using undetermined coefficients, what am I doing with the particular solution? Guessing. Yep. I guess a solution, and then I have some undetermined values in there that I have to figure out. All right. So I'm usually saying to myself, I know what it's going to look like. I have a constant input source. So I have a DC voltage source, let's say. So I know I'm going to get a DC current. So I guess that it's a constant value. And then I have to figure out what that constant value is going to be. Then I have to find the total solution by putting the two of them together. All right, that sounds like a trivial step, right? I put the two of them together, but what's one part of this step? What's something I always have to do in that third step? I have to use the initial conditions to solve for whatever unknowns I've got left. All right, there's always going to be a couple of those. Okay, all right, so in general, our differential equations are always going to look like this guy, non-homogeneous, and they're always going to have constant coefficients. In other words, the things in front of the derivatives are always going to be constants. They're not going to be functions of time. All right, those from a circuit come from resistors, capacitors, inductors, whatever. Okay. On this side over here, the side without the derivatives is always going to be a driving force, some input to the system. All right. If it's equal to 0, that means there's no inputs to the system. So in this case, this circuit right here, would this be equal to something? This guy's going to have an RC. There's going to be some RC differential equation that comes from the circuit on the right. Is this differential equation going to be equal to 0 or something other than 0 for this circuit?
0.
It's going to be equal to 0. Yeah, there's in this case,
there's no independent power source.
Yep, no power source here. Right, there's nothing to drive anything going on here. All right, so this guy's going to definitely be equal to 0. All right, so if we get rid of the x of t and we set it equal to 0, that is our homogeneous equation. Okay, and that gives us the transient response. All right, so a couple of things we talked about. I don't need to focus on this too much, right? But if I have, there's always as many derivatives in the equation as there are storage elements. And there's always as many exponentials in the solution as there are derivatives. So that means in a second order system, we're going to have 2 exponentials, right? We'll start talking about those today. When I have 2 exponentials can be 2 complex exponentials, right? If I have 2 complex exponentials, what do I always get? What do 2 complex exponentials always combine into? One sign, yeah, one sign or cosine. Okay. All right, so we're going to make that connection a little bit as we go. All right, so the inputs that we're going to consider are these 3. Okay. This one here, this a times u of t, that looks like a constant, except that it has this u of t. So I defined u of t the other day. U of t is what I call the unit step. All right, unit step function. We could probably say a whole lot about it, but it's not the most interesting thing in the world. The unit step, what is it? If I tried to draw u of t versus time, what would that look like? Constant value beginning where? At t equal to 0. All right, so he would basically be 0 before t equal to 0 and then jump up. So I said u of t is equal to 1 for t greater than 0 and 0 for t less than or equal to 0. All right, and I could probably put my equal to piece in either one of these. All right, it's a little bit unclear exactly what's happening at t equal to 0. All right, I'm not going to get too hung up on that. All right, other types of inputs I might consider: exponentials and cosines and sines. Okay, now the one thing it's useful to remember is these 2 things are kind of the same. All right, and that's, again, we're gonna use that framework. Exponentials and cosine sine, closely related, basically the same thing. Okay, all right. So the other day we looked at this guy, right? So I figured out an equation for this. I called this voltage source Vn, and I solved for the voltage on this capacitor. All right, which I put into this form. I called this Vn. I called the input to it X, and I called the output Y. And the output is the voltage on the capacitor. All right, and I put it in this form here. What did I have to do to get this equation? What rule did I use to get this equation? KVL, right? I used Kirchhoff's voltage law to get to that. Okay. All right. I said my input was a cosine wave multiplied by u of t, which basically just means that the input is 0 before t equal to 0, and then it's something after that. Okay. All right. So to approach this, right, there's two steps we had to follow. The first step was this transient response. All right. So what do I do for the transient response? So I modify the equation here, right? This was the original equation I had this form. Okay. And I modified it over to this form. So if I have the equation in this form that I have right here, what do I do to get this transient response? I have to guess. What do I guess for this? What do I guess is my transient response? Y sub c. Well, what do I always have for what does my transient always look like? What kind of function is my transient always? Exponential. So I guess c e to the st, where I got to make sure I have one caveat to this, right? What caveat should I have? C is not equal to 0, because otherwise I just picked 0, and that's a trivial answer. Doesn't make any sense. Okay. 0 would satisfy this equation, but I know there's a transient response. I have to choose something that's going to satisfy this equation. So I put that in there. So that gives me d by dt of c e to the st plus a times c e to the st equals 0, like that. Okay. Now, what's the derivative of e to the st? Yep. Yeah, I bring an s down. So this guy becomes s plus a times c e to the st equal to 0, right? I just took the derivative in group terms there. So I did that slower the other day. I'm skipping a step there, right? But you should be able to follow from this line to this line pretty easily. So when I look at that, I basically have three numbers, right? I have a times b times c equal to 0, where this is like a, this is b, and this is c. Three factors multiplying each other equal 0. So any one of them can make that expression equal to 0. But what do I know about c? Can't be 0. That was one of the choices I made. What about e to the st? Is e to the st ever 0 for any t value? No, for no finite value of t, at least, is that ever equal to 0. So it has to be the case that s plus a is equal to 0. So s is equal to negative a. So whatever number a is, a could be the number 6, right? Whatever I get there solves that. This thing right here we called a characteristic equation. All right. That kind of comes from the fact that parameter a is somehow characteristic of the system, right? In other words, if it was an RC circuit, that guy would depend on the R and C values, right? So it depends. It's somehow characteristic of the physics of the situation. All right. So we got that. What I did then is I said, okay, well, what about the particular solution? And I went through this very quickly, and I'm not going to really go through it in detail today. But if I have this, all right, this was our original equation. What I said is I guessed something of this form right here, b cosine omega t plus phi. What does that mean in words? If I guess this as my steady state solution, what am I guessing about my solution? Output has the same frequency as the input, right? But potentially can be what? Two things can happen to that input as it makes its way through the system. Get larger or smaller in amplitude and get shifted left or right. Okay. In other words, I can't put a cosine into a system as my input and get an exponential as my output. Okay. So basically, if I put a cosine in, I get a cosine out. So, but there can be a shift and a change in amplitude. So what I said is what you'd have to do is you'd have to guess this value and plug it in for y right there and right there. If I plugged it into that differential equation, I would get this nasty looking expression. Then I'd use some trig identities to take the cosine omega t plus phi and the sine omega t plus phi. I'd break them up into things where I had the sine omega t's and the cosine phi's separated. I would have this whole big expression. And I would do that both for this guy and for this guy. Then I would go through and I would look at my expressions here and I would say, well, it looks like what I have is a cosine omega t plus 0 times sine omega t on this side. And I'd start setting basically different terms equal to 0. So I would look at this and I would say on the left side of this expression, I have a coefficient on my sine omega t that has to be 0, a coefficient on my cosine omega t that has to be a. Go through and do some more trig, and ultimately I would end up with the fact that this is my particular solution. All right. There's a lot of trig identities, there's a lot of manipulation, a lot of algebra, and it's ugly. Okay. All right. Without going through all the details on that, because I don't really care about the details of it. You guys will get lost in it if I lecture on it. All right. And it's not that important anyway. Suffice it to say that it's ugly. Okay. So where we ended with is that Euler's identity gives me a different approach. Okay. So if this circuit right here, I could build this in the lab, right? I can get a function generator and hook it up to an RC circuit. And I said, this is a super common circuit. I gave this circuit a name. If I'm trying to measure the voltage across here, anybody remember the name I gave this circuit the other day? Well, I talked about an ADC converter connected to it, right? But I gave this, that's just the R and C together, a separate name. I said this was useful with an AD converter. It's what? Low pass filter. Yeah, you got the key part. The low, yeah. In other words, what this guy is low pass filter. We're going to talk about what that means, but this guy filters low frequencies and gets rid of high frequencies. All right. And that's a good thing when I'm sampling signals, when I'm hooking things up to microcontrollers. We'll talk about that more, but I'm just trying to suffice it to say this is a pretty common circuit because of what powerful stuff that enables us to do. All three of these circuits are equivalent to each other here. All of these are equal to each other. All right, what have I done? I've used Euler's identity here to say that if I have a cosine omega t, I can think of that as two rotating vectors. In other words, if I put my multimeter right here, or my oscilloscope, and I looked at the voltage across these two things, what would the voltage look like right here? It would look like cosine. All right. So in reality, yeah, I would see cosine. If I look on the oscilloscope, I'd see a cosine. But in my mind, I can think of it as two rotating vectors. But that's not real. That's not what's really happening, right? And if I look at that voltage goes up and it goes down, it goes up and goes down. But I can think of it this way, right? And that makes things a lot easier for me. All right. In particular, I'm going to use this guy right here. I'm going to say, instead of thinking of this as a cosine omega t, I'm going to think of it as the real part of a e to the j omega t. All right. And we're going to use that approach. So what I'm going to do is I'm going to try to analyze a different circuit. Okay. I'm going to say, what if my input to the circuit was a complex exponential? So if I look at this here, I have a e to the j omega t. I have the real part of it and the imaginary part of it. These two circuits are the same exact circuit. Okay. So what I'm going to do is if I look at this, if I have two sources like this together, and I wanted to forget that there's reals and imaginaries and all that sort of stuff. But if I had two voltage sources together like this, if I used superposition, how do I analyze a circuit like this with superposition? Remove one source, solve with one of them in there, and then vice versa. So what I'm going to do is I'm going to say, well, if I wanted to get the response from this circuit, or from this source, I would analyze with this one and then turn the other one off. What I can also do here is I can say, well, let's put them both on together, and then we'll take the real part of the solution to figure out what our actual answer is. Okay. So here's what we're going to do. We're going to go back to this original problem. I'm going to try to solve this again. I want to use complex exponentials. All right, so let's follow. I got a basic approach that we're going to try to follow. All right, so I got basically 5 steps here that I'm going to walk through, which they're pretty straightforward in general here, but I'm going to basically guess back to this original system, right? A cosine omega t plus, or A cosine omega t u of t, same basic thing. But what I'm suggesting with this here is we said that we should guess that the particular solution is B cosine omega t plus phi. That's the same thing as guessing that it's the real part of B e to the j phi e to the j omega t. Now you should be able to expand this out, right? B e to the j phi e to the j omega t. You should be able to expand that out to say B e to the j phi e to the j omega t is B times cosine omega t plus phi plus j sine omega t plus phi. Like that. The real part of that is clearly this. Okay. We're going to basically guess that this is our solution here. And we're going to take the input, which was A cosine omega t, and I'm going to convert my input to say it's the real part of A e to the j omega t. Then what I'm going to do is say, you know what? I'm going to forget about this whole real part, imaginary part thing. I'm going to basically solve this equation right here. A e to the j omega t equals this thing. And then I'm going to take the real part of the result. Okay. So the process is going to be this. I'm going to guess this is my solution. I'm going to take that non-homogeneous equation. I'm going to somehow get it to the complex domain. Then I'm going to substitute B e to the j phi e to the j omega t into that equation. Then I'm going to create 2 equations where I'm going to solve for the magnitude and solve for the angle. And then I'm going to take the real part of everything. Okay. So let's walk through that. All right. So the first part, A cosine omega t equals this whole thing right here. Okay. So I got to convert this into complex exponential form. So I'm going to say this guy becomes A e to the j omega t equals A dyp dt plus yp, like that. Okay. Now, because I had a cosine input, I'm going to guess that my output is a cosine. So I'm going to put into this thing. So step 1 is to guess this solution. This was step 1. Step 2 is to basically take this guy and put it in the complex exponential form. So what I'm going to do is I'm going to say my yp for now is just going to be B e to the j phi e to the j omega t. And my last step is going to be take the real part of whatever I get. Okay. That's how we're going to follow this through. So what do I do next? Now that I have that, what do I do next? So I'm guessing this is my solution. Once I've guessed that's my solution, I said my step 3 was substitute it into the equation and go from there. Okay. So I need to substitute this into my equation, my differential equation. So when I substitute that in, what's going to happen? So we're going to guess yp is B e to the j phi e to the j omega t. So I guessed that. So what happens here? What do I do next? Yeah, I put that in and I start taking derivatives and such. So I say d by dt B e to the j phi e to the j omega t plus A times B e to the j phi e to the j omega t, like that. Okay. Now what? Got to take the derivative there. What's the derivative with respect to time right here? What's the derivative? B e to the j phi e to the j omega t. Don't let the j's and the omegas fool you, right? It's e to the at. E to a constant times t. So if I have e to a constant times t, what's the derivative? What's that? Take the constant out, right? Bring the constant down, right? So this guy becomes b e to the j phi times j omega times e to the j omega t plus little a times b e to the j phi e to the j omega t. All right, help me simplify that. I got some common factors there, don't I? How can I group terms here on the right side? Yeah, what terms are clearly in every entry here, and this guy and this guy? B e to the j phi and e to the j omega t is common, right? So I can say b e to the j phi e to the j omega t times j omega plus little a like that, right? If I distribute that out, these two are equivalent. Okay, so let's look at this for a second. I got a e to the j omega t equal to that expression. One term is there on both sides, right? Which term is on both sides of the equation? E to the j omega t. That's actually pretty nice, and that's actually where all the wind comes from. What have I taken out now? I have a equals b e to the j phi times j omega plus a constant. Taking out the time dependence, that means the differential equationiness of it has just disappeared. All right, that's the nice thing. There's no time dependence now. And that's actually, it kind of makes sense because the only things we're really solving for are this magnitude b and this phi here. Okay, so I've gotten to this relationship here. If I write it down over here, this is I get to this a equals, right? A equals b e to the j phi j omega plus a. I've gotten to this result right here. Okay. So my step 4 is to solve for the two unknowns. So it's pretty easy for you guys to get lost in the math. What the heck am I doing here again? What am I trying to solve for? Which two unknowns? B and phi, right? B, the amplitude of that cosine, and phi, the phase shift of that cosine. All right. So this is actually two equations. How is it two equations? It looks like one equation. Not quite. So let's look at it this way. So what do I not know? So I got b e to the j phi. I'll write it this way, equals a constant a over j omega plus a constant little a. It's a complex number, right? So a complex number here, I've got a magnitude and an angle. So can I look at this like this and say there's a magnitude equation and there's an angle equation? Okay, so and that's exactly what there is. There's two equations here. All right, so let's look at the magnitude. All right, so I had b e to the j phi equals a over j omega plus little a like that. I can take the magnitude of both sides of that. Okay, magnitude of both sides of that. B e to the j phi. What's the magnitude of? So if I take the magnitude of two complex numbers, right? That's the same as the magnitude of a times the magnitude of b. All right. So b times e to the j phi. What's the magnitude of b? Well, b was just a number, a real number, right? So on this side over here, I have b times the magnitude of e to the j phi. What is the magnitude of e to the j phi? So let's remember, e to the j phi is cosine phi plus j sine phi, right? What's the magnitude of that? 1. All right. So that gives me that b equals the magnitude of a divided by j omega plus little a. So I got a real number divided by a complex number. The magnitude of a is a. What's the magnitude of that number on the bottom? J omega plus a. How do I get that? So take the magnitude of that. So what's the magnitude of, I have j omega plus a. What's the magnitude of that going to be? Square root of little a squared plus omega squared. Boom, I'm done. All right, no trig really involved in that at all. Okay, that's a lot easier, especially when these are numbers, right? It becomes a lot easier to walk through on them, right? No trig involved at all. Okay, so I got my magnitude now. My magnitude depends on the magnitude of the input and apparently what frequency I'm at. All right, so that's something we're going to explore a little bit later in terms of in the project. We're going to talk about that. All right. There's also an angle equation. All right, so let's say I've got, so let's write it the same way. B e to the j phi equals a over j omega plus a, like that. All right. B and a are both real numbers. What's the angle of a real number? 0. Should be 0. Now, I could have -1. What's the angle of -1? 180. All right. Technically, though, that should have been somehow lumped into the phi. All right. So in this particular case, my amplitude on my cosine that I guessed better be a positive. You can never have a negative amplitude. All right. It doesn't make sense to have a negative amplitude. If I had -3 cosine omega t, like that, the amplitude, what is the amplitude of -3 cosine omega t? 3, not -3, right? What's the angle of -3 cosine omega t? This guy would be 3 cosine omega t plus 180, right? The amplitude of it's 3, all right? But the angle of it's 180 degrees shifted. And you can think about that, right? If I showed you, here's cosine, all right, like that. Let me draw my cosine better. All right, if that's cosine, what's minus cosine look like? It's just flipped over, right? So it would look like this. Right? If this is cosine, this would be minus cosine. So they're shifted 180 degrees from each other. But the amplitude is still 3. Amplitude is always a positive number. All right. So I don't want to get too confused in that right now. That wasn't what I want to talk about. But whenever you have, what always screws people up is when you have a negative real number, that negative is not part of the magnitude. That negative is an angle. Okay. All right. So what I want to do here is I want to get another equation from this. This equation here, there's an angle equation. So in other words, I can look at this and say the angle of B e to the j phi has got to be equal to the angle of A over j omega plus A. Okay. So when I have two complex numbers multiplying each other like this, it's the angle of B plus the angle of e to the j phi. If B is a complex number, what's its angle? Or sorry, a real number, positive real number. What's its angle? 0. This is 0 degrees plus, what's the angle of e to the j phi? Phi. Right, not a trick question, it's just phi. Okay. What about this guy? Angle of A divided by j omega plus little a. That's going to be the angle of A. What about on the bottom there? So what do I do with that? Do I add those angles? Angle of A and the angle of the thing on the bottom? Subtract. So it's the minus the angle of j omega plus little a. All right. What's the angle of A? This guy. 0. Yep, that guy's 0. So I get that phi is equal to the negative angle of j omega plus a, which is what? Negative tan inverse of omega over a, like that. Okay. So what I found then is that b was equal to this, phi was equal to this. My last step is to take the real part of the result. Okay. So I found b, I found phi. The real part of b e to the j phi e to the j omega t is my result. So I plug all that in here and I end up with a cosine at the end. Okay. So this part, I went through the basics here of what the steps are, right? So I basically have these, sort of 5 steps, right? I guess a cosine, and then I really at that point start to look at this dynamic phasor thing. And then I say, okay, well, we got to convert the whole equation into complex exponential form, which means I got to take that sinusoidal input and put it in complex form, right? So what I did was I said a cosine omega t becomes a e to the j omega t. Then I basically substitute b e to the j phi e to the j omega t into it. And then I get an equation for the magnitude, an equation for the angle. And then I take the real part of this. That's the process. Now, everything is best seen with an example, right? So there's an example video. I already posted it. I mentioned it in the homework, which basically goes through this guy right here. All right. It's about a 20-minute video that walks you through how to get to this final solution right here. All right. So when you're solving for b, this guy is my b. This guy is my phi. All right. Those are the pieces that I sort of solve for in there. So I had cosine 5t as my input. This guy has the same frequency, but is different magnitude and different phase. Okay. So that video walks you through exactly how to go through that, and walks you through how to put it into MATLAB too. Yeah. Oh, it should be, yeah. One of those should be a derivative, right? If you look, it's the first one. That should be dy by dt. Yeah, good catch. All right. So you walk through in there, but what's this going to look like? What would this thing look like? If I had to plot y of t here, what is that going to look like when you put those things together? I could think about the two separately, right? 3.5 e to the negative 5t. What's that going to look like? Yeah, the old finger picture basically stops, right? He starts out high and then he ends at 0. What about this guy? What's he going to look like? How do these two relate to each other? Cosine 5t versus this guy here. 1 over square root of 2 cosine 5t minus 45 degrees. How do those two relate to each other? Second one's been shifted 45 degrees. Which way? To the right. And amplitude got smaller. Okay. So if I look, and I have this there in the video, and I see it nicely on my screen, but it doesn't look as great on yours, right? Oh, okay. So the yellow here is the input, right? This guy is the cosine 5t. The blue is the output. Okay. So notice when I look at this thing, I can see, and this is from the video, I snipped it, where this is, I'm trying to show the phase difference. There's a 45-degree difference, right? The output is 45 degrees to the right. Okay. And it's a little bit smaller, right? It's 1 over square root of 2 smaller if I look at the amplitudes carefully, right? Where's the transient response? At the beginning, right? So the whole thing I'm looking at here is a combination of the steady state plus the transient response. But the thing about the transient response is it always ends up gone by the time I'm done. All right. And so it becomes 0 eventually. And that's what happens here. And so if I look at this, right, so the amount of time that passes here is relatively small. Okay. If I had this circuit up in the lab, you know, when you're doing a lab, right, you hook up a function generator to some circuit, the power's on for a long time, not milliseconds, right? So usually you're connected to that circuit for many minutes or maybe even hours longer than the transient lasts. So very often, what we just did here, this analysis, where I use these complex numbers to deal with steady state, a lot of times that's all you look at. All right, so you're going to spend most of the time in 2112 focused on using this approach. You're not going to talk about the mathematical details like I just did. You're going to use the mathematical details. But because of this fact, the really important thing was this step here. When I used complex exponentials, time disappeared from the equation. That turned essentially that differential equation into an algebra equation, all right, and made the analysis really simple. So because of that, what we end up with is, if I have a cosine input to a system, I don't need a differential equation at all. If all I really care about is the steady state solution, essentially all I have to do is to use something called impedance, all right, which you're going to talk about if you haven't started yet in circuits 2, where I can basically just look at the circuit and I can use basically a version of Ohm's law with capacitors and inductors to be able to skip over writing any derivatives. All right, and that becomes a much simpler way to analyze it. It doesn't capture the transient piece, but usually we don't care that much about the transient part, because what's true about the transient goes away. All right. Now, in certain cases like control systems and things like that, all we care about is sometimes the transient response, and it matters a lot. But for most systems, most circuits, we don't really worry that much about the transient. All right, and so this allows us to sort of skip over that. All right, so again, there's the video I posted goes through that in excruciating detail. I shouldn't say excruciating, that doesn't make it sound good. All right, it's a 20-minute example. It's got MATLAB code in it. All right, and you can walk through and see how to solve it for that particular case. All right, but it basically just walks through the process that we use. All right, so last time we had something like this, where I've got another first order, I've been given an initial condition here, all right? So I wanna walk through the steps on this guy. I said 4 u of t. So if I have 4 u of t, what does that mean my input looks like? If I had to draw it as a function of time. 4 u of t, what does that look like before t equal to 0? 0, and then after t equal to 0, it's 4, okay? So my input looks like that. All right, so I want to follow through with my process here. There's my differential equation. This guy here. Somehow the RC values are such that this guy's 0.01 dy dt plus y equals 4 u of t. All right, so sometimes the way I write this is for t greater than or equal to 0, I get rid of the u of t and I say this just becomes 0.01 dy by dt plus y equals 4. Right? Those two expressions are equivalent. If I say for t greater than or equal to 0, I can get rid of the u of t. All right. So my 3 steps: transient solution, right? That's the first one. What's the second step? Particular solution. What's the third step? Put them together. All right. Combine the two to get the total solution. All right. So to get the transient, I have this. All right. What do I do next? That's I got my homogeneous equation. In other words, I get rid of the 4 u of t, set that equal to 0. Yeah, and so for the transient, what am I going to guess? Yep, I guess y sub c equals big C e to the st with C not equal to 0. Okay. So I'm going to go through this process. I'm going to get 0.01 d by dt of C e to the st plus C e to the st equal to 0. And I'm going to end up with 0.01 s plus 1 times C e to the st. All right. Same basic process I did before. All right. What's true about C and e to the st? Are they ever equal to 0? No. So what's equal to 0 here? I got three things multiplying each other. Which one of them is equal to 0? The first one, right? So I have 0.01 s plus 1 equals 0, or s equal to what? Negative 1 over 0.01, which is what? Negative 100. No. One thing that better always be true about any differential equation you write, if it came from the universe that exists that we know, what's going to be true about all the coefficients there? 0.01 s plus 1. What's true about all the coefficients? I guess the coefficients come straight out of this differential equation, right? What's true about all the coefficients in that differential equation? What must they be? They better be all positive. Why? What would happen if they were negative? What would be true about this s value? This s value is currently negative. What does that mean about my exponential? It goes to 0, it decays. If I ever get that I have e to the positive number t, what's happening then? That's not a transient response. That's a destruction of the universe response, right? That means that the energy on the capacitor or whatever is going to become infinite. All right. That's not going to happen. All right. If that ever did happen, the capacitor would explode, right, before the universe destroyed itself. But that should never happen. If you get a negative ever, all right, in this differential equation or any of those coefficients, you screwed something up. All right, that's a hint for 2112. All right, if you ever get negatives in those differential equations, you've done something wrong. All right, you can never, ever have that, because then I'm going to get an exponential that explodes rather than decays. And my transient response better decay, or else it's not transient. Right. All right, so anyway, particular solution. All right, particular solution. What do I do here? I have to guess again, right? So if I have a constant over here, what do I guess is my steady state solution, yp of t? What do I guess? Should be another constant. And let's say, I don't know what it's going to be. I'm just going to say that it's some constant b. All right, and it's applied at time t equal to 0. Right? So what do I do next? Well, this is the undetermined coefficient, right? The thing that I don't know is b. Now I have to determine it. So how do I determine it? Now I plug this into the expression, right? So I get 0.01 d by dt. And I'm going to say for t greater than 0, greater than or equal to 0, right? 0.01 d by dt of b equal or plus b equals 4. In other words, I put this into that expression and I get this. All right. So looking at that, what's the derivative of a constant? 0. So this guy goes away. And I'm left with the very simple answer, b equals 4. All right. Now, I'm not always going to have that, right? If I had some coefficient on this term right here, then yp would have been some different value. B would not have been the same as the input, right? So don't say that it's always going to be just the same as the input. It's not necessarily. I got to look at the coefficients carefully on the equation. All right. So I have now, at this point, my total solution is that. Okay. I have 4 plus c e to the minus 100t, and I put this u of t multiplying it which basically means that y of t is equal to 4 plus c e to the negative 100t for t greater than or equal to 0. Okay. Now, what do I do now? Still got one unknown term here, right? My initial condition, I need to figure out what c is. So back to what I said at the very beginning, my initial condition is that y of 0 is equal to 10. So how do I use that here? Yeah, plug 0 in. So I say y of 0 is 10. That's equal to 4 plus c e to the negative 100 times 0. What's e to the negative 100 times 0? 1. So I end up with c is equal to 10 minus 4 or 6. So I end up with the fact that y of t is equal to 4 plus 6 e to the negative 100 t for t greater than or equal to 0. So if you look at the way that I have you entering this in MATLAB, it usually ends up with something like this. Okay. I usually ask you to give me y sub c, y sub p, and y. A combination of those two things. And then so in other words, I have you give me the total solution, the particular solution, and the transient solution. Okay. So 6 times exponential negative 100t. That's this guy. This is my transient. Now, a new command that I added here is this guy ones. I mentioned at the very beginning of the semester, ones is going to give me a vector or a matrix of ones, the number 1. So it's kind of like my unit step thing here, right? So when I say ones of size t, what does that mean? What's going to come out of this expression? Ones of size t. Everything in it's going to be the number 1. It's going to be a vector that has all the number 1, and it's going to have the same size as whatever the t vector is. All right, so it looks just like the t vector in terms of how many rows and columns it has, but all that's in it is the number 1. Okay, and for all of these problems, I'll give you the t vector. All right, I'm not letting you choose the t vector. We'll talk about that for the project. I'll always say, here's the t vector for that. Tell me what yp and yc are. Okay, then I put them together. So looking at this picture right here, you guys tell me which one of these is y sub c, which one is the transient response, which one's the steady state response, and which one's the total response. So I got the blue, the yellow, and the red. Which one is which? Which one is the steady state, the particular? The red one, right? This guy is yp, right? Just a constant, equal to 4. Which one's the transient response? The blue. Oh, this guy is y sub c. All right. He decays to 0 entirely. This is my total solution. Right? It looks like the sum of yp and yc. Okay. So I ask you to plot all 3 of those. And I give you an exact page in the book where this command comes from. Notice what I did. If I want to plot all 3 of them together, t comma yc, t comma yp, t comma y, that plots them all. All right. In the assignment, I point you straight to the page where that's located. All right, so you can copy that command over. But this is exactly the way it would be done. All right. So all of the solutions you have on homework 5 are going to look just like this, right? Where you're going to be basically entering these guys all separately like that. All right, questions about that? First order differential equations, you guys should be on top of that. All right, at this point. We're going to cover also second order stuff. All right. So second order and first order systems, right? First order systems, 1 energy storage element. Second order systems, 2 energy storage elements. First energy storage element, first order systems where I have 1 energy storage elements. I know that if I have no sources what's true about all of the voltages and currents in the circuit with no sources if I have a first order system? If I wait long enough, what are all the voltages and currents in the circuit going to be if I have no sources? 0. If I have sources, what's going to happen is everything's going to get to some constant value. In a second order system, I have 2 energy storage elements and they can interact in weird ways. Okay. Which means my transient has 2 exponentials because I always have as many exponentials as I have energy storage elements. But it's possible that this energy transfer back and forth between the 2 elements can lead to a really strange interaction. Okay. Where possibly the transient never stops. All right. So you guys ever seen, I don't know if they show that video anymore. It was old black and white video of a bridge that is sort of in the wind starts kind of oscillating, right? And eventually the bridge breaks apart. That's a system where the transient response, it's a dynamic system, wind blows and it causes the bridge to move, right? So the structure has a time dependence to it. And the transient response doesn't go away in that particular case, all right? That can happen in real systems. So an example here, I'm going to say I got a pendulum here. All right, so simple pendulum, where I'm basically saying what I got is some device where I've got a pinch point up here, right? And I'm going to set it where I've got it right here. So this is the pivot point. Okay. And I say, let's take this ball and let's pull it. So this is 20 degrees away from the center line initially. Okay. Now, what's going to happen in this particular example? If I did this, what's going to happen? So we should go to negative 20 degrees, you're saying? And then what? So yeah, so it'll come over to here to negative 20. So let's say this is negative 20 degrees. In an ideal pendulum, what's it going to do? It's going to go to 20, negative 20, 20, negative 20, and it's just going to keep doing that forever. In reality, it's not going to do that, most likely. Why not? Yeah, where's the resistance here? Yeah, there's probably some in the air. The big thing is probably going to be the friction up here in this pivot. This is probably where the biggest losses are. Like if that's a really tight grip on that bar, right, that's spinning, you're going to lose a lot of energy as this guy moves. So I move this guy to 20 degrees. Once I move this ball to 20 degrees, we say this thing has potential energy, right? Right? It's pulled up to some height. I let it go, and then energy goes to kinetic energy as it spins. Okay. What's going to happen if there's absolutely no losses in this system? I started at 20 degrees, it's going to go to negative 20, and then it's going to go back to 20, and then back to negative 20, and it's just going to go back and forth forever. Let's say I just hold a little bit tightly to that pivot point. And I started at 20 degrees. What would I expect it to do when it swings to the left side? Less than 20 degrees, a little bit less, right? And then when it goes back to the other side, it'll be a little bit less than it was on the other side. And then a little bit less, and just eventually, what's it going to do? Eventually go to 0. Eventually, it's going to stop because all the energy that was stored up in it initially is going to be gone. It's going to have been dissipated as heat up in that pinch point. I would call that, if I looked at this particular system, right, if there was no losses in there and I looked at, let's say, the height of that ball, what I would see is the height would trace out a cosine. And the velocity of the ball would trace out a sine. Okay. If I were to put a little bit of losses in this system, they'd be going like 20, negative 19, 18, 7, negative 17, right? It would look like what? It would look like a transient. And how would that transient look? Not an exponential per se, right? But what would it look like? It would look like this. Yeah, it would go like that, right? What I would call what you know to be a damped response. Okay, it's trying to look sinusoidal, but because of the losses in the system, it's decaying. Now, what's going to happen if I make the losses in this thing really big? So if I hold this guy right here and I let it go, but my losses are really high, just goes straight to a final position. What's it look like in that case? An exponential. All right. So everything, so in this particular case, I get systems and second order systems. I always get exponential responses. But without any losses, what I'm going to get is a sinusoidal response. A sinusoidal response is what? Two complex exponentials, right? So the natural response of that system, if there's no losses, is basically for the energy to move back and forth. So in my pendulum, it goes from potential to kinetic and potential to kinetic and potential to kinetic. If I had a circuit, right, it would go from energy in the capacitor to energy in the inductor and back and forth and back and forth. Right? If I were to look at this, and so I have this, if you want to watch it, there's a YouTube video that compares the pendulum to this circuit, right? If I look at this circuit where I have an RL and a C, if I increase the resistance from 0 to 10 ohms, at 0 ohms, what I see is the voltage on the capacitor is cosine and the current on the inductor is sine. And they just track each other like that. And as I increase it, it becomes underdamped and eventually gets to an overdamped response. Okay. And all of it dissipates pretty quickly. So it all comes down to the losses in that system, right? I think that physicality means a lot, right? Because very often I actually do want to get these sinusoidal responses, but that's really hard to do in a physical system. So I give you a circuit on the very last problem on homework 5, where you actually really do get a cosine output. Where would you want to have that? Where would you want to get a transient response that actually gives me a cosine? It doesn't go away. Any ideas? There's as many of those circuits in this room as there are people right now. What's that? Well, what? There's a sine wave in a power outlet at least, but what kind of application do you think where you'd want to have a circuit that makes a sine wave? Well, you basically plug a voltage source into a light, a radio, right? There's an oscillator in your phone, right, that's creating a waveform, so you can transmit something at 2.4 gigahertz or whatever. Right. So if I want to transmit something from my phone, I need to make a sine wave that allows me to be able to send something out at a particular frequency. So in that case, I get a circuit whose transient response doesn't die. All right. Nature doesn't like that. Right. There has to be some way to basically overcome the losses in that circuit to make that happen. I don't want to go down that road, but it's a pretty common thing that I somehow do want to make systems. They don't talk about those in 2112. But this is more of a math class. So I'm focused on the math of the fact that there is a way somehow to make this R go to 0. So I can just slosh energy back and forth. Okay. All right. If I have a second order differential equation, again, I'm not focused on the KVLs and the KCLs in this class. You're going to be given differential equations. Okay. Differential equation is going to look like this. So if it's second order, basically what I'm going to say is it always has some form like this, where these coefficients are always going to be constant. And our solution still looks like this, particular plus a homogeneous. But what's true about this homogeneous response here? What's our homogeneous response? It's going to be C1 e to the S1t. Plus what? C2 e to the S2t. There's always two pieces to that transient response. There's two exponentials. They could be complex, all right? So that's what we're going to try to deal with next time. I'm going to summarize it here, right? But we get to this thing called the characteristic equation, and there's basically 4 different options for what the transient response can do based on those roots. So we're going to apply the complex numbers here to solve for this. We'll look at that on Wednesday. All right. So that's it for today. Again, I'll send